So our goal today is to measure the charge to mass ratio of the electron. And the procedure that we're going to use for this is one that you've seen in class now a couple of times, and is one that we've alluded to in previous labs. And the background really is this fact that a particle that's moving in a magnetic field will exhibit circular behavior in the directions perpendicular to the magnetic field. So to just go through that quickly, because again, you've probably seen this 3 or 4 times, let's pretend that I have a charged particle that's moving upwards at some velocity v, and I'm going to actually not kid myself, and I'm going to say this is really an electron, and so it's going to have some charge that we're going to call minus e. And it's by definition, of course, that the number e is actually something that's going to be positive, and so we really want to say that the charge is minus e, even though colloquially we often refer to e as the charge of the electron. So if the particle is moving upwards, then I know I can use the right-hand rule to determine the direction of the force, right? So if this were a positively charged particle, the force, of course, let me write it down, which is QV cross B, right? For a positively charged particle, V up, B down would create a force to the left, but since it's a negatively charged particle, the force is going to be to the right. And of course, the magnetic force is always perpendicular to the velocity, and so I can expect to have circular motion. And I can also calculate that the magnitude of this force is going to be given by the magnitude of Q, which is just E, the magnitude of V, and the magnitude of B, because I've set the problem up so everything is perpendicular. And since it's moving upward and the force is inward, then I'm going to get these beautiful circular motions in the directions perpendicular to the magnetic field. And if I set it up correctly so that there's no velocity up or down in this case, then I really have circular patterns. And that's a spectacular prediction, right, of the magnetic force, and it's something that we're going to dramatically see in the lab today. So even though the background for this is something that you've seen before, there's real promise here to see something dramatic, because we'd like to actually see these circular paths when we put electrons that are moving through an external magnetic field. So if I do the algebra out, I get that the force F equals ma leads me to this expression, which is one that you've derived in 240, which eventually gets me down to this expression, which tells me that the radius of that circle is going to be proportional to its velocity, inversely proportional to the magnetic field, and the constant of proportionality is the ratio of the mass of the electron to the charge of the electron. Right? And this is also something that's really cool, because if I want to think about measuring either the mass or the charge of something so small, right? Microscopic isn't even the right word for it, right? Something so fundamental. It's amazing to think that I might be able to do this by looking at macroscopic things that I can measure, right? So the radius, of centimeters and magnetic fields that I can generate in the lab, and velocities that I can generate in the lab are going to lead me now to be able to measure something about particles that we have no hope of ever seeing. Right? There's no optical telescope that's going to allow us to see optical microscope. I'm sorry, that's going to allow us to see an electron. Right? So the fact that the properties of the radius of that circle and the velocity of the electron and the strength of the magnetic field, this relationship is going to allow us to extract that ratio. And that ratio is the thing that we want to measure today, right? So even though it's 3 symbols, an M, an E, and a line, we're going to treat that as sort of one parameter, right? That's the one thing that I want to get out of the lab today. And I can do that in a bunch of different ways. And I think one of the fun things about today's lab is that we're going to allow ourselves to get a little bit creative, right? You can take that formula and you can linearize it in a bunch of different ways, right? So R is a function of V, R is a function of B, V is a function of B, V is a function of R. And no matter how I linearize it, I'm going to end up with some combination that has that ratio of E over M in it. Well, sometimes it looks like M over E, but I always have that ratio E and M coming out. Now, of course, there's always going to be something else included in that ratio, right? So if I'm say doing the case where I'm going to plot R versus V, I still need to know what the magnitude of the magnetic field is in order to take the slope of that plot and turn it into the ratio of E over M. But that's something that I know how to do, right? So today, we're gonna, because of that creativity, I'm not gonna tell you which plot you need in order to measure E over M. But this is a conversation that you're gonna have with your lab partner pretty early on, because you want to think about which of these plots is going to minimize your systematics, which of these plots is going to be something that's nice and easy to linearize, which of them is going to harness the stuff that you know how to do, right? So you are going to need at least one great plot, okay, that gets you to this measurement of E over M. But because we can do this entire lab just by making one plot, we really have to be careful about our uncertainty analysis today. And so there are only a couple of uncertainties to propagate. It's your choice, of course, how you set up the experiment to make sure that you propagate them the correct way. But you really have to be careful with your uncertainties, and as I like to say, you need to be confident in your uncertainty analysis in order to really be successful today. Okay, so let's head to the lab and see how we're going to use those Helmholtz coils, which we looked at last week, to create magnetic fields where I can now test I can study the trajectory of electrons as they travel in circles. Now today is a big day. I don't know how many people have come to me in their first year of physics and said, when do we get to use this equipment, right? And this week is the time that you finally get to use it. As you know, from what we were just talking about, our goal today is to figure out what the charge to mass ratio of the electron is. And so I'm going to have to produce some electrons, and then I'm going to have to manipulate them in order to figure out, in order to answer the question. We have a lot of equipment, but that equipment basically boils down to three different parts. And as you're getting oriented with the laboratory equipment this week, you really want to make sure that you're looking at these three different parts independently to make sure that you're measuring the right thing. So the process is we have to generate some electrons, then we have to accelerate those electrons, and then we have to change the trajectory of those electrons. So generating the electron means that we have to turn on a filament inside this tube here, which is going to heat up and therefore allow us to eject electrons. You'll note that in the lab manual that monitoring the filament current is one of the most important things that we're doing, because if that filament gets too hot, we're actually going to start to melt it rather than just liberate some electrons from its surface. The way I have it set up here, this bottom power supply is the one that's that's actually going to generate the current that's going to be going through that filament, and I have an ammeter that's set up that's going to allow me to monitor it, right? And you can see you've done enough with digital multimeters now that you can recognize that this is set up to measure current because the input is going into the amp side, not into the potential side. Once I generate those electrons, that is, once I liberate those electrons from my filament, I then have to accelerate them across a potential difference in order to give them some energy, so that way that they can move, right? I won't have a magnetic force unless something moves. The way I have this set up, this blue power supply is the thing that's going to be generating that potential difference, and this is one of our big power supplies that goes up to many hundreds of volts, because I want to give those electrons a lot of energy. I'm going to be monitoring that potential difference with this smaller digital multimeter, right? This one doesn't measure current, right? And so it's the only one in this setup that's not going to be used to measure current. But it's going to tell me how big is the potential difference across that capacitor that's going to be accelerating my electrons. Right? This one will not have any current, right? Because after all, it's a capacitor, and what I'm going to be taking advantage of is the static electric field in between that capacitor in order to accelerate my electrons. The last thing I have is my Helmholtz coils, and now we studied these last week, right, when we were talking about generating magnetic fields. Inside the middle of these Helmholtz coils, I have a region of space where the Helmholtz coils are generally homogeneous. In order to, with a magnetic field generated by the Helmholtz coils are effectively homogeneous. The strength of the magnetic field is determined by the current through these Helmholtz coils, and I have another power supply that looks just like this one in the back here. I couldn't fit them all in one frame. That's how much equipment we have today. That power supply is going to generate the current that's going to flow through these Helmholtz coils, and then I'm going to monitor it using this third digital multimeter. Okay, so just to go through those stages again, I'm going to generate electrons. I'm going to liberate them by heating up a filament. That filament can't exceed 4.5 amps. That's going to be monitored by this multimeter and generated by this power supply. I'm then going to accelerate that across a potential. That's a capacitor, and so I'm not going to be measuring the current. I'm only going to be measuring the potential difference. That's going to be generated by this power supply and monitored on this digital multimeter. And then my magnetic field is going to be generated by a third power supply, and I'm going to monitor that current, right? Because it's the current through the Helmholtz coil that's going to generate the magnetic field. Now, when you turn these things on, we're going to always start by turning on the filament so that we generate some electrons. Then I'm going to accelerate them across the capacitor to give them some energy. But of course, before I turn on my actual magnetic field, I need to cancel out the magnetic field due to the Earth. Now, to do that, we have these great old-fashioned, they're great technology. We have these compasses that help us to determine the direction of the magnetic field. So if you put the compass on the table, you should be able to find the direction of the magnetic field. And what you want is for the axis of your Helmholtz coils to be in the direction of that magnetic field. There are lots of knobs and things to turn here, right? You can turn the apparatus, you can move this up and down, but it's important to have the magnetic field from the Earth going through the axis of this apparatus, because the first step in taking data is we have to cancel that magnetic field out. In a second, I will turn the lights off, and I'll show you closer what's happening inside here as I change the different knobs. But you want to do this configuration where you set up the axis of the magnetic field before you ever turn any of the equipment on. Once you start turning the equipment on, we're talking about serious amounts of current and potential difference in this apparatus, and you do not want to be leaning over the apparatus, moving the knobs while you have any of this turned on and connected. Okay, so let's zoom in and take a look at what's happening inside that bulb when I turn the electricity on. So here we are zoomed in looking at the bulb itself, and right now I have everything turned off, but I'm going to turn things on one at a time to show you what the procedure will look like. So I'm going to first start by turning on the filament potential, and you can see that now there's sort of a glow that's on the right-hand side of the bulb. You can't quite see the filament because it's heading sideways in the frame, but you can see that something there is hot, right? It looks like an old-fashioned light bulb, right? You heat things up and it generates light. Of course, I don't see any electrons coming out yet because I haven't turned on the capacitor, right? And so I don't yet see the stream of electrons coming out. So if I turn on the capacitor, now I can see that blue stream of electrons, and that's of course because the electrons themselves aren't blue, right? I mean, electrons have no color. Little quantum chromodynamics. Anyway, they're blue because there's a mercury gas inside the tube that the electrons are hitting, and that's what's actually emitting that blue color. So this is what the stream looks like, and I've aligned my apparatus so that that stream actually comes out straight, right? And that's because I paid attention to what the direction of the Earth's magnetic field is, and so I expect my stream to come out straight. So the next thing I'm going to do is I'm going to turn on the the Helmholtz coils. And you can see immediately what happened was that stream of blue electrons is now going around in a circle. And lo and behold, it actually is coming pretty close to hitting one of those posts, which now looks a little bit green. Okay, so some of the tubes are better than others, but the post should have something on it that phosphoresces a little bit green when the electrons hit them. Now we have to trust the manufacturer because you should neither touch anything in this apparatus while it's on or the bulb ever, right? So you're going to have to trust the manufacturer when they tell us how far apart those different things are. But I do want to give you confidence that if I change the current through the Helmholtz coils, indeed turning it up, wrong button. If I turn it up, the circle gets a little bit smaller because the magnetic field is greater. If I turn it down, the circle gets a little bit bigger because the magnetic field is weaker. If I turn up the potential difference in the accelerating potential, I can also affect the radius. Turning up the accelerating makes it go faster. Turning down the accelerating potential makes them go slower, and that also changes the radius. So the thing that you're being challenged to do in this experiment is, of course, to find out what kind of data is going to give you the best measurement of this E over m, right? So do you hold the radius fixed and change the current in the accelerating potential? Do you keep the potential fixed and change the current in the radius, right? What do you do to find the right slope in order to calculate the E over m? Anyway, this is one of our coolest experiments, and I hope it has not disappointed you so far in seeing that, in fact, charged particles do travel in circular paths around in external magnetic fields.